Hi, everybody. Thank you for joining our call today. Hopefully, it will not last for 2 hours, but we do have a lot of very important stuff to decide on and to discuss. On this note, I'll probably just pass the mic to Maxim, and he'll just proceed with everything he needs to discuss.
Hi, everybody. Today we have quite important talk with a lot of all-stars guys joining in, starting from those who invented the concept of single-use seals, like Peter Todd, and many other things, and also to those who use them to define new layers on top of Bitcoins, later named LNPBP, like Giacomo Zucco, and of course, myself. And also everybody else who were hardly contributing and criticizing and peer reviewing different proposals related to single-use seals, client-side validation, and RGB over the past years. And the reason for that is that several years ago, we actually did an implementation of the single-use seals primitive, which I will describe in several moments what it is and why it is important. And in Rust, and we are happy, we were quite happy with that implementation. On top of that, we started building new layers, including RGB. And then we started bringing RGB to the Lightning Network, also an effort that lasted for a couple of years. And today we are moving closer to its completion. And together with new updates coming to Bitcoin Network, like Taproot, we decided to update that part to use Taproot as well. And we ended up with a very interesting situation where we found out some trade-offs that have to be addressed with existing single-use seals, with the way how we do it today. And potentially we found a way how we can improve that. So the structure of today's talk would be that I will spend about 5 minutes explaining what single-use seals is for those who join our call and don't know what it is. It wouldn't be impossible to explain, so I just will refer to other talks and calls before for them to Google. Then I will move to the explanation how the single-use seals used today and work today. Again, very briefly, assuming that people are aware of that. If they are not, I will again reference to the standards and code to dig into. And the point of that explanation is just to remind everybody who participated at this call, how it's actually structured today. And then we will move to the main part, which will occupy probably the most of the time, where I will be explaining first issues that we met. We will discuss them. Then I will explain what are solutions that we have found so far. We will discuss them, criticize, decline, propose new ones. So basically, the most of the call should be a discussion part with some slides on the screen that will help to structure that discussion. And I will ask Olga to help me with moderating that discussion part. So let's jump in right into the presentation. And first of all, I would like to say that this will be a very hardcore technical call, and the target audiences that will understand something from this call will be probably peer reviewers of client-side validation, single-use seals, and RGB protocols, contributors to the reference Rust implementation, the current one of these protocols, maybe those who would like to work on the independent or alternative implementations using other technological stack to be up to date with actually how the single-use seals has to be implemented and how they evolve over the time. And also those who would like to write some technical notes or articles about this kind of technology. The background. So basically what single-use seals are about. There was a big developer core devoted to the single-use seals. Yeah, here it is on the YouTube. This is the link. So I just invite everybody who is interested in what the fuck it is and how it works to listen to it and to dig into that. It provides a lot of references to the original research, which actually comes from Peter Todd, who is the guy who designed, invented, envisioned this stuff. And single-use seals, in few words, is just a form of applied cryptographical commitment and a certain promise to create a commitment to a certain message in the future. And it's more advanced primitive than simple commitments with cryptographic hash functions or timestamps. And we have even some comparison that shows how they all differ from each other. Basically, the single usil system, the most feature-rich form of the commitment, and it allows you to fulfill the actual commitment to the message in the future at a certain point of time. Why do we need this primitive? Well, basically because it addresses the main problem of double spending or double committing. So with a single usil, you can build a sequence or chain of commitments where you can prove that the history of this change over the time was unique and there were no alternative history created. Basically, it leverages the concept of ledgers or proof of publication layers like Bitcoin blockchain to create a client-side validated version of unique histories that can be proven against certain ledger data to be the only source of truth. On this slide, I would like to explain a very important and hardcore terminology about single usils. Peter, he had invented the terms that the single usil is closed over certain message, which caused a lot of confusion even to myself and others, not talking about the broader audience. And this is a visual explanation why we say that the single usil is first defined. So we have this blue ribbon on the screen in our hands, and then we close this single usils over a certain message, and this action can be done only once. And once it closed, we can always verify that it is indeed closed, and some certain message is contained inside, at least a commitment to that message. There are three main single usils procedures. We can generate or define a single usils, which means that we do a promise of the future commitment to a certain message without doing that actual commitment yet. Then we fulfill that promise by closing the seal over that specific message, as it was shown just on the previous slide. And then we can verify multiple times, anytime we need, that the seal was indeed closed, and it was closed only once and for all of the parties who can witness this seal. So that's the ground definition of the main single usil terminology. As you have seen, the single usil is a very generic concept, not specifically related to Bitcoin. It's a cryptographic primitive which can be applied to many areas. And today we will talk only about its Bitcoin application. So now we are moving to Bitcoin single usils. And with Bitcoin single usil, there is the main way how we can define them is to specify certain transaction output basically, which consists of transaction ID and the output number as a single usil. And this definition doesn't touch the transaction itself. The transaction is mined. It is a part of the blockchain. The output should not be spent at the moment of the definition. And that's how we create a single usil. It's a very simple procedure. We just say to certain audience that this transaction ID plus output number is our single usil definition. And those who are interested in this promise of the future commitment should follow this transaction output, UTXO, and whenever it is spent, as shown on the right side of the slide, they will know that the seal was actually closed over certain message. And again, the transaction that closes that seal is actually the transaction that spends that previous output, previously unspent output. We call this transaction a witness transaction. From on-chain analysis, there is nothing that can be guessed that this transaction has some special meaning related to single usils. Only if you have known that the seal was defined as the UTXO of the previously spent transaction, and if you have an exit transaction witness consisting of certain proofs and commitment data, you will be able to verify that the seal was closed over a certain message. And basically, this proofs and commitments data should be generated from the spending transaction and should be related from to that spending transaction. And the question is how we can do that relation, because we need to define this relation in a very deterministic way, such that we can't communicate to different parties different forms of relations. Otherwise, we will be able to double spend or double commit to something, and it will break the definition of the single use that we have. So, skipping a lot of information, there are only two parts of the transactions where we can put a commitment to a message outside of the transaction. Basically, two parts where we can put the witness of that single use seal will close over a certain message. The first is the transaction input that actually spans the single use seals that we have defined. And in transaction input, we can use only script sig or witness field, depending whether we are using a pre-SegWit or SegWit transaction. And on the output side, we can use a script pub key of certain output, but for using script pub key, we need to define also an algorithm how we will know uniquely and deterministically which of the script pub keys from which of the outputs is used to create the commitment. So only two options here. And these two options can be leveraged with either pay-to-contract or sign-to-contract commitments. They are well known for quite a long time, originally described in the Eternity Wall company article, later bought by Blockstream. And pay-to-contract commitment is actually a homomorphic modification of a public key from a script pub key, where we commit to the message by adding the value of the integer value of the hash of that message to the public key. And sign to contract is a more advanced form of a commitment where we commit in the signature, which can be put to the script, to the SIG script or to the witness field of the input. And we do not modify the public key with which we are signing. We modify the nonce of the signature, and this nonce is actually specific for the signature. And it's more advanced form of the commitment because it doesn't require us to store the trick to be able to spend that actual output, because commitments goes to the transaction input. So this is a background of these two things. Again, I'm not going to explain it over this call. I'm just saying that these procedures do exist, and if somebody do not know them, they can refer to the internet and read more about their details. So the difference between these two is basically they have a very different trade-offs. Pay-to-contract requires keeping info on the client side, because without this info, the client side the owner of the transaction wouldn't be able to spend it later, because he wouldn't be able to create a proper signature. And the private key has to be treated in the same way as a public key to spend that output. On the bright side, it's basically very similar and easily combined with the Taproot, which is in fact a pay-to-contract protocol by itself. Basically, it does the same tweaking procedure for the public key to create the whole structure of the Taproot specific data, and we can quite easily combine it with the new Taproot form. The sign to contract have a distinct trade-off. First of all, it doesn't require you to keep the data to be able to spend output later, because there is no output to spend. It goes into the input. So you can decide and create the trick at the moment you spend the single use seal. And however, it is less compatible with the hardware wallets. So in our work on the RGB and single-use seals, we decided that pay-to-contract commitments are more compatible with the hardware wallets, which is important. So let's start from that. It was Giacomo Zucco in 2019, and it was approved by all of us. Giacomo, thank you for all of that. Now we have all that headache.
Yeah, I can add that the reason you are mentioning is the true reason, is the reason which is correct. I also have an incorrect reason. I thought it was not compatible with Lightning security, but that was debunked only a few months later. So I have also a wrong reason to do that. But you're welcome.
Yeah, but anyway, it will come down to the fact that we can't live without pay-to-contract commitment. That's why it's very nice that we have one. So it was actually a right decision to have. But it is not obvious from the very beginning, and that's why. So let's say that we have a Bitcoin single-use seals defined with some certain transaction output and closed over a message with a pay-to-contract commitment. To be brief, we call them TXO P2C Bitcoin single-use seals. So transaction output based with a pay-to commitment. And here again, we have a seal definition, which doesn't change, and we have extra transaction witness of the seal being closed over the message that is committed into the witness transaction, the transaction pending single-use seal, using 3 different procedures in 3 different steps. First of all, we tweak a public key or a set of public keys. It's defined by LNPBP1 procedure, and it's an extended pay-to-contract commitment protocol. Then we define how we will pull this set of public keys into different forms of transaction outputs, which may vary from the pay-to-public key or pay-to-public key hash or witness public key hash up to a very complex scripts. And we had to cover all of that complexities because without that, we will not be able to be compatible with the Lightning Network, where all the outputs of the commitment transaction have script-based outputs. And finally, we have to determine a specific transaction output that contains the commitment. And for that, we have this LNPBP3 proceeding. So basically, we ended up with the 3 standards designed late in 2019. The first one, LNPBP1, it describes how to deterministically put a pay-to-contract style commitment into not just a single public key, but even a set of public keys, because some transaction outputs may contain scripts that have multiple public keys, and we need to be sure that we are not able to create a double commitment using different public keys and spread it to different parties to prevent double spend. Then we had LNPBP2 that explained how to extract this set of public keys from a specific transaction output, and LNPBP3 that described how to detect output that must contain a commitment. And for that, it was a very long discussion in 2009, lasting probably for the most of the year. And we ended up with a protocol that uses both transaction data and extra transaction data as the most efficient form how we can prevent both on-chain analysis and at the same time avoid fee adjustment when we would like to avoid it, and also split different commitments related to different protocols across different outputs. So we used 2 things. First is a fee of the transaction, which is actually indirect data that can be derived from the transaction graph, not transaction itself, which created later problems with implementation, because basically now to verify the single-use seal, you do not need, you wouldn't be able to do the verification by just reading the transaction. You have to have the full access to the transaction graph to be able to compute the transaction fee. And also, the second factor was a protocol ID, which was specific to a protocol under which the commitment is executed. And this protocol ID is not necessarily protocol as application level protocol like RGB. It's more like asset identifier, such that multiple assets can be combined in the same transaction. And we were happy with that until in the same 2019, we discovered the problem that there is nothing that prevents from defining the same single-use seal, the same transaction output multiple times. And while we can try to deny that, while we can try to ask to avoid that, the wallets and the software vendors, we can't actually prohibit that, but we can ask them not to follow this bad practice. It actually happened that this is not a bad practice. This is a good practice and a feature of the protocol of the single-use seals, because it allows us to reduce the DXO set size. So whenever we need to add some asset as a single-use seal from RGB or create other form of single-use seal-based protocol, we do not need to create a UTXO, a new UTXO. We just reuse the existing UTXO, which may contain already other single-use seals. So we don't want to get rid of this problem. We would want to find a solution how we can continue use single-use seal with this condition. And the answer was developed as LNPBP4 standard in early 2020. We found how we can actually combine commitment to multiple messages under multiple protocols into a single commitment and put that single commitment as a message over which we close the single-use seals. So it's single-use seal. So basically we ended up that a multiple RGB assets or timestamping data or any future client-side validation protocols can be combined under a single commitment of the single-use seal closer. So that was quite a good advancement. And with that advancement, we had a more complicated scheme when we introduced the structure we call Core, which contained basically a tree of commitments under different protocols structured into a single message over which we close the seal, and which we commitment to that message we put into the transactional put defined by LNPBP3, modifying the script pub key with the LNPBP2, and embedding that commitment into specific public keys inside that output using LNPBP1. The original LNPBP4 that we developed were simple than what I described today. So we started with a linear serialization of all the commitments into just linear structure and then taking hash out of it. Later, independently, I have found that, and also when I met Peter in September, once again, he confirmed that he was thinking about the same thing for some time. We have found that LNPBP4 can be enhanced by using Merkle trees. So you don't need to keep the linear structure, because with the linear structure on the client side, you have to keep amount of data proportional to the number of the actual assets and commitments you have to store. With a Merkleization, you just reduce that to the logarithmical function over the number. So, for instance, you will need just 512 bytes per 65,000 of assets on the same single-use seal, which is a huge increase. It comes with some cost, so you will have a slight increase in the verification time, but here we are more interested in the scalability in terms of storage, and also it brings the advantage of better privacy, because instead of, we can allocate a lot of slots for this multi-message commitment, and we can fill them with the entropy such that the other party wouldn't be able to guess how many assets we actually had transferred. And we were happy. We made an implementation, and we used that in implementation in RGB, and it was the very happy part of this presentation. As a summary, basically, we ended up with a Bitcoin transaction output single-use seals using pay-to-contract commitments defined by these standards. So that's basically ends the introductory part of this talk today. So it's basically I'm setting the stage and reminding everybody about the history, how we get to the situation that we are in today. And unfortunately, today we need amendments to this procedure because of Lightning Network and Taproot. It happened that Lightning is, in fact, a thunderstorm, because originally it seemed that it's not that hard to integrate single-use seals and RGB on top of them into Lightning. We have witnessed set of problems initially in 2019, which we actually solved. And then Today, when we are moving towards the release, we witnessed a completely different bulk of the problems, which I never named in the publicity before, and I would like to name them today. So let's start. During the last year, while we were working on the Lightning implementation of RGB, and also on the wallet implementation of RGB, not dependent on Lightning Network even, we have witnessed more drawbacks of the pay-to-contract commitments in general. And let me name those drawbacks. First of all, when you have a transaction created by multiple parties, which is the common case for the Lightning Network, especially when we move to channel factories and other multi-peer setups of the Lightning channels. It is also true for coin join and pay join transactions. It is also true for multi-sig transactions when we use a number of signers or number, even if you have a single signer, but you have a set of hardware wallets and you create a multi-sig across them. You basically need to keep you need all participants to modify their private keys and keep that information. Because if the pay-to-contract goes into the transaction output that they control, they wouldn't be able to spend it without keeping that tweak of the private key. And first of all, if you use hardware wallets, not all of them will support them, so it will be really restricted. And of course, even more, if you are a participant of multi-peer protocol like coin join, pay join, Lightning Network, it will really complicate the protocol itself. The second problem is in Lightning Network, we found that channel funding is actually an interactive protocol. And when we create a channel funding, we need, and there is a case that two parties provide the same asset using RGB into the same channel. They have to, or even different assets, but coming from the same single-use seal, they have to reveal the information on other assets as well in order to create a joint state transitions. And it actually will leak a lot of privacy data. So basically, when you add some output to the Lightning channel funding, you will end up exposing most of your asset data, even if you don't plan to use that assets in the Lightning channel, which is also quite undesirable from the privacy perspective. And finally, if the quite common use case of Bitcoin is when you provide it with a Bitcoin URL or a Bitcoin address and ask to pay to that address. And unfortunately, if you will have an RGB assets on the address from which you are paying, it might happen that you will be forced to tweak the output that you are paying to. And basically, at the end of the day, it will have a different address. So the receiver wouldn't be able to see the funds coming, and you have very hard user experience time explaining that to people. And this might, the worst part of the story that it happens unpredictably, because when it happens, of course, if you create a payment, our assumption was that you will always have a change address and you will just put the tweak into that change address. That's not how it works in the multi-asset world. Because if you will have multiple assets on the same UTXO and you have just two outputs, and let's say you have 10 assets on the UTXO, there is 95% probability that you will need to tweak both outputs. Because basing on the algorithm that we have, which detects which output has to be tweaked per each asset, you will end up with a high probability that both outputs has to be tweaked for different assets. And basically with that, you wouldn't be able to do a pay to address. So basically you have a UTXO, you allocated one asset, then another asset to it, then another asset, then another asset, then you try to pay to an address with your Bitcoins on that output, and you will end up that wallet says that this operation is not possible. Unpredictable. And this is really bad from the user experience perspective. So basically, pay to contract is not that doesn't have that usability that we expected. Even more, there are more problems with a pay-to-contract for the Lightning Network. Some of these problems were mitigated by us, or we found the solution to them. First of all, Lightning Network used lexicographic output ordering. It's not compatible with the pay-to-contract because basically you change the order of outputs, and when you change the order of outputs, you need to adjust the fee. When you adjust the fee, you need to change the output amount, which will again cause you to reorder outputs, and you will again not match the pay-to-contract output you need to tweak. So you will enter the endless cycle of these readjustments. The other part is that Lightning Network deterministically derive keys for outputs, which doesn't work when you apply a tweak to the key. And finally, Lightning Network has a very strict algorithms for defining fees, and the pay-to-contract mechanism of putting the commitment into specific output also not very compatible with that. These problems are actually addressed because we need to match changes to the structure of the transaction, but basically we can say that Lightning channels operating RGB in the channel will have a custom transaction structure. And by that, we mean that no lexicographic output ordering will be applied. There will be additional non-deterministic derivation with the tweaks, and the fees will be defined by a different algorithm. That requires surgical changes to the Lightning Network, but it is doable. What is not doable and not mitigatable, the issue that we discovered over the last 2 weeks, is actually the need to interactively create state transitions to operate RGB assets in the channel when you have more than a single asset in the channel. And the leak of the privacy from this procedure, when you need to expose also the assets which do not participate in the channel funding. So last call, I was doing a presentation on Bifrost. What is Bifrost? Well, it's a generalization of Lightning Network created to address a number of problems with the existing Lightning Network outside of the scope of single use that I was just talking about. Basically, it's a way how you can add Taproot, Miniscript, and many other sweet things into Lightning Network by breaking back compatibility, but maintaining the same liquidity network. And the question is, how can we fix all those problems with the Bifrost? Well, actually, only partially. Some of them can be fixed, some of them cannot be fixed. And unfortunately, because it uses Taproot, it brings more problems. For instance, in Lightning Network, there are outputs that can be spent without any signature. You probably don't know that, but this outputs called, they introduced by Anchor Outputs feature of Lightning Network. And after a certain period of time, these outputs can be spent by anybody who knows about that output without providing any signature. So basically, you can't have a public key there, and you will have a really hard time of putting commitments and tweaks to the output that doesn't contain a public key. And with a Bifrost, you have even more than 2 parties because Bifrost generalized concept of Lightning channels into multi-peer channels, allowing channel factories and more complex setups. And it's even harder to orchestrate pay-to-contract commitments. So 2 weeks ago, I asked myself what to do with this pay-to-contract problem related to the Lightning Network and also wallets and all the setups that I described. And so the RGB community kept pressing me on when RGB and Bifrost. So I was really under stress. And I said that some time ago we discussed that signed to contracts are also working well. So let's back up to the signed to contract, update the RGB spec. We have plans to have a signed to contract, RGB moving to signed to contract commitments in the version 2, but probably we should do that now. Unfortunately, it is not that easy. Signed to contracts, they have their own drawbacks. First of all, it became apparent that they are not compatible with pay to Taproot script path spendings. Why? Well, because Taproot allows future script versions after certain soft forks which are not present today. And these features, custom scripts may use completely different types of signatures or no signatures at all. And we can't be sure that we will be able to apply sign to contract commitments into these future script types. The second problem is that when we do a multi-sigs, the main setup for multi-sig environment in the Taproot probably will be MuSig, second version. And and sign to contract is basically not yet compatible with a MuSig 2. At least we need much more research to find out how we can introduce a sign to contract between multiple parties in a safe and secure way into MuSig 2. So MuSig 2 itself by itself it took 2 years of research, and such it's not yet fully implemented even in Bitcoin Core. So adding sign to contract to it, it's a huge effort. Also, sign to contract is even worse compatible with the hardware wallets. And it may be different set of hardware wallets which are compatible with one and incompatible with other. And today also we have no implementation for Schnorr-based signatures for sign to contract, even in Bitcoin Core and any other library. So it's not that easy. Moreover, sign to contract can be used with Bifrost in all of the cases. Because first of all, that anchor outputs, which I just described, they have a non-signature path spendings. We can fix that by asking that basically this path spendings requiring no signature can basically be spent with any signature of the channel participants. So it wouldn't create a security vulnerability, but again, it's a drawback. Again, we have no ready sign to contract scheme with a MuSig 2, which basically is needed to create a funding for Bifrost transaction. And one of the very hot features of the Lightning Node implementations today is the ability to use Lightning Node with some hardware wallets plugged into the servers or the boxes running the node itself. And again, sign to contract wouldn't be compatible with that. So I spent some time considering other alternatives, like using for Taproot outputs an annex field, which is the signed part of the witness. It wouldn't work because with the future soft fork, the use of annex will change most probably, and we will end up that some outputs created today will be not spendable in a year from now. So you create a channel or you do transaction, and later you find out that this transaction can be used because of the consensus rules. And basically, why? Because it can conflict with the future soft forks on consensus level. The other option is using dump extra witness stack item, which goes before Taproot control block item in the witness. Unfortunately, it may conflict with the some script logic, so it's also non-deterministic, and you will end up that you have to modify your scripts, and if the scripts are deterministically defined between multiple parties, you will break protocols based on them. It will also add to the blockchain space consumption, because basically you put the commitment in as an additional data item. And the most worst part of that story is that because witness data are not signed when you create the spending transaction, this commitment may be removed or replaced or added by miners, and you will add up that miners basically will be able to interrogate into your single seals, which we don't like to. Basically, no way to do that. So I ended up with this table describing the drawbacks of both approaches, when one approach can be used and when the other can't be used. And the summary of that table is that pay-to-contract can be used with a Lightning network and only some of Bifrost transactions. It can be used with a pay-join and coin-join. It can be used with complex multi-sig setups. And it can be used when you have a Bitcoin URL and pay-to-address requests. Sign-to-contract, on the other hand, cannot be used with other transactions in Bifrost channels with the hardware wallets. and with some weird outputs of Bitcoin transactions which can't be spent without a signature. For instance, you create some puzzle and you would like somebody to solve it, and the solution of the puzzle is basically a specially constructed transaction witness that spends that output, and there is no signature required there. So basically, again, we end up that we have a very different trade-offs here. I'm skipping the slides because on the discussion we will go through all of them again. And the question was that, can we use both pay-to-contract and sign-to-contract? And it came that actually potentially we could. But to use both pay-to-contract and sign-to-contract, we need to signal at the transaction level which specific scheme is used, because otherwise we will have a double spend problem. We need to signal on a per spend output basis, because you can spend a multiple single use seals with the same transaction. So it should be a transaction input that actually signals how the commitment for this single use seal that is closed should be put into the spending transaction. And this signaling can be part of the transaction witness, because the most important, it can be modified by miners. So the only way to signal is to use end sequence number. And there is a solution, quite complex, how end sequence number can be leveraged to do that. But before moving to that part, I would like to start the discussion session on the part that we already discussed, namely the critics of pay-to-contract, sign-to-contract approaches, and what can we use with them.
This is bad. One first thing that comes to my mind is that it seems like the use cases you listed among the ones you cannot use with the sign to contract are more exotic and less common than the ones that are impossible under pay to contract. So if I compare this list, very like high level without any serious reasonment, it seems like it's worse to rule out the use cases in the left case. On the other hand, the idea that you can choose and signal which one of the two schemes you're using per input per UTXO spent base may also take care of some of the drawbacks of pay to contract, because some of the drawbacks are caused by the signaling mechanism that we have to use to specify which output. And if we already have to signal which scheme, maybe we can just put into that signal also which output and not just which scheme, avoiding the fee trick, which was always a little bit ugly and also breaks a lot of things that you listed. So yeah, these are my first thoughts, but not an easy answer, not an obvious answer.
Well, I would directly respond, can be put into a sequence signaling some other information than the binary selection? And my answer, no, without sacrificing certain privacy and chain analysis qualities. And I will explain later why. So we can signal binary option without sacrificing chain analysis properties and privacy properties, but we can't put more than a bit of information into a sequence number.
1 bit. So you
One
cannot
bit.
do like 2 or 3 just to confuse it.
No, unfortunately.
Huh.
But also, if we will use just sign to contract, we will end up that we can't use RGB with a taproot over the lightning, which is very unfortunate, because in some of the cases it wouldn't be possible to do that. Some of the parts of the channel structure, not all of them.
Yeah. It seems objectively more overwhelming the kind of sacrifices we have to do with sign to contract. Actually, yes.
Hey, here's your one question regarding your hardware wallets. Is it just existing hardware wallets or hardware wallets in general, which makes it difficult to support signed contract?
I'm not sure that my opinion is the right one on this matter, but my general assumption is that it's more because of the design of the hardware wallet than the specific hardware wallet implementation. Because when you have a hardware wallet, its main task is to sign something. And the algorithm of the signing is embedded into this hardware wallet. And one property of a secure algorithm, that the algorithm creates a secure nonce used in the signature. And the nonce is the part that we need to tweak with the sign to contract. So basically, if we will provide a hardware wallet with a tweak to a nonce, basically we break the security of the hardware wallet itself.
Okay.
Well, so with hardware wallets, I mean, it should be able to just do custom firmware that works differently on that. Like, if doing a tweak to a nonce is secure in general, it's the way I guess I'd put it is you can come up with a custom hardware wallet firmware that'll tweak it just fine. There's no issues there. But something I want to just generally ask though is, did you look into op return outputs?
Yes, we have them as one of the options, basically on this table, the last row, last column. So basically, there are only one thing that is compatible with hardware wallets, and actually, the op return commitment scheme is a part of the current standard. So you can create op return instead of pay to contract with the RGB.
But it would make fingerprinting or chain analysis easier, right?
Yeah. So basically, different trade-offs with the three different schemes.
Now, granted, I mean, from a chain analysis point of view, like op return, because we don't actually need to put any intelligible data into it, you're not getting that much information over what's actually happening.
Yeah.
All you see is that there are outputs with op return. You don't know why. They could be for open timestamps for all you know. Like, there's tons of schemes that use the same, 32-byte opaque hashes. So this may not be a big concern.
But it reduces the anonymity set.
Sure, but it doesn't reduce it as much.
Because basically it is not only RGB which uses op return, and it's not all that RGB transactions will use op return, just some of them. So you have really hard guessing what kind of op return you have in the transaction from the chain analysis point of view.
My concern with that long term will be that right now a lot of other stuff use op return, including open timestamps, because it's simpler and it's obvious. But most of the things that don't need anti-double spending protection and single-use seal and just need aggregated timestamping like open timestamps, they may eventually have a reason to move to sign to contract or pay to contract over the years, especially in an environment of high fees. And they could, because they will not have all the drawbacks that single-use seal mechanism have. So while, I mean, right now, probably an op return will not be that expensive and will probably hide into a crowd, which is pretty good. But eventually all this crowd, since they don't need all the things that we do with the anti-double spending protection and single-use seal, they may move away to sign to contract stuff. So,
but by that time, hardware wallets, maybe custom hardware wallets, may be designed. Because we are not alone in this fight with the hardware wallets, better custom hardware. Liquid and Blockstream, they have the same issue. They're using basically sign to contract scheme with a Liquid. And part of the problems that I know from Andrew Belstra, who described me the problems with both pay to contract and sign to contract. So there is a high probability that there will be wallets that will be able to parse custom tweak data. The problem is that, like, when you spend single-use seal, and there is certain assets linked to this single-use seals through RGB, for instance, the hardware wallet should describe you what actually you do with the tweak you are creating, because you can lose your assets if there is a malware that change the actual tweak you apply. And so the hardware wallet should receive the additional patch of the information, which will tell that it is USDT being spent on this address, and it should display it, parse it, display it, and then get the information and make sure that the tweak is actually exactly fulfilling this promise from that information. So it's really custom hardware wallet that would be able to do that. But pretty much the same customization is required to work with the liquid assets, because the same thing applies to them. They also exist as tweaks to the keys inside the transaction. So hopefully by the time when op return will extinguish, we will have hardware wallets that support better processing of tweaks, both in pay-to-contract and sign-to-contract.
But you just mentioned that tweaking the nonce is a general security problem.
There are two different unrelated security problems. The first, that tweak may lead to the loss of certain value. For instance, it will spend RGB or liquid assets. It's a first security problem. So the user should not just send a tweak to the hardware wallet and hardware wallet apply to public key or signature without making sure that this tweak has a certain value preserved in sense.
Okay, but this is potentially solvable.
This is potentially solvable, yes.
Yeah.
And the second problem is that the nonce, especially for the Schnorr signatures, has to be really random.
Yeah.
But if you solve the first problem, you instantly solve the second problem. Because if the hardware wallet ensures that the tweak doesn't modify the nonce in some attack way, but instead is a commitment to certain spending of some extra assets, extra transaction assets, which you can't just create in such a way that it will modify nonce in a attacking style way, then the both problems are solved. So they are basically solvable with a custom hardware wallet hardware.
So
the secure way to implement that kind of nonce would be to have the hardware wallet come up with a nonce, and then a tweak is then submitted to it, which then it derives, which then the final nonce is then derived from its own nonce plus hashed with the tweak in some way, in some defined way where the randomness of the hardware wallet derived nonce is guaranteed to be securely mixed in with the proposed tweak.
Yeah, true.
So
and you just got to come up with a scheme for that and standardize it.
That should work.
But how do you guarantee that the nonce is not accidentally then used
by
more
hardware
than one?
wallet? So if the nonce is not known to anybody other than hardware wallet, that we can't create a tweak that will be an attack vector to the nonce. Right, Peter?
Well, I mean, in fact, it's even better than that, which is provided that the way that they're combined is something that's, where the output's uncontrollable, then you're fine. Perfect example being if you just go hash the hardware wallet generated tweak with the, submitted tweak, you're good.
Yeah.
Right.
Because have a multi-party nonce, which is more secure.
Yes, yeah, it's basically a multi-party between your computer and the hardware wallet itself.
So that solves.
I can check because I recently had a talk with Stefan Snigerer from Spectre. They have the Spectre DIY, and I think he implemented already something like that. So I can make you the intro or talk to
him. That would be good because basically we need the hardware wallet support. We actually talked to Trezor and Ledger, and they confirmed that basically we can achieve the presentation of extra information. So that's that problem with the nonce, because we were talking about beta contract commitment, but we can provide the additional data such that the hardware wallet will display to the end user, and also be able to take certain computations on the data to make sure that the tweak matches those data. So we can basically write that in C, and it will be run on the wallet hardware without modification of the hardware of the Trezor and Ledger. So we have that information. We know that Blockstream uses hardware signing security modules for Liquid, with all these sign to contract tweaks working on them. And we have the, again, as you said, the context that can help with the other hardware wallets. So basically, it's not an unsolvable problem. It's a problem to be solved, but there is a clear, secure path for it to be solved. And before that, we can use just op return fallback for those wallets who are not yet supporting all of that.
Okay. So what are the deal breakers then we have in this table? The hardware wallets is maybe.
Well, for me, it seems that if we use all the three options, then basically we will always be able to create. If we have some UTXO with a single seals, we can deterministically be sure that we will be able to spend it, no matter which setup we are using. Is it Lightning, Bifrost, Taproot, hardware wallet, signed spending, pay to address, or whatever else? We have sufficient options to cover all of these use cases. If we use just one or two, even two of them, we will have situations when we will end up with a UTXO that we can't spend without losing some value. And the only question is, for me, for now, is how we can signal which specific option is used using the available transaction data on chain without exposing any additional information to chain analysis. And I think that there is a solution with end sequence, which actually the next part of the presentation. But before that, I would like to make sure that we are all on the same page of the previous part.
Just as an aside with hardware wallets, remember that in these protocols, since there is data we have to go store, in addition to all other obvious problems with hardware wallets, you also get the issue that you can be held for ransom by, someone who's attacked your computer and then deletes that data and saves their own encrypted backup copy or whatever. Mm-hmm. So in fact, a proper hardware wallet is going to also need to have storage on it to then independently store copies of the data you're going to need in the future to go spend your asset. So, it is not trivial how much work it is to get useful hardware wallets in these protocols.
Fortunately, that's not only hardware wallets. You can leverage distributed storage protocols controlled by your, for instance, seed phrase. So
but the issue is that in a protocol like this, all those distributed storage protocols, because they run through your computer, which could be compromised, you can't assume that at the moment of spend or signing or whatever, that protocol isn't by itself compromised. So really, you do need a hardware wallet that itself, has storage on it to, properly mitigate all these problems.
But you can take your paper wallet seed phrase, go to another computer, and if you run some weird, you go just to another computer, restore the data.
But if your computer is compromised, the moment when this is created, that protocol may have never actually run, right? Suppose the protocol is, something very simple, like you upload your copy to Google Drive. That may not actually happen if your computer's compromised at the moment of signing.
Right.
So in a normal system, your Bitcoins would be protected. In this case, they aren't, right? Because you can be held for ransom to be able to spend it later.
So basically, hardware wallets should provide the storage for all the client-side validated data.
Yes.
Or at least be aware of it. And
or potentially, verify proof that some external provider has stored it. But honestly, SD cards these days are dead cheap and, you can easily buy one that stores terabytes. So,
Yeah.
Relying on micro SD cards might actually be the better way.
This discussion is completely orthogonal to the commitment scheme, am I right?
Yes, but it's still important to bring that point up.
Yeah, sure. Just to be sure that this is something that we never seriously consider until now, but is not really connected with the choice between the commitment scheme variants. Okay.
Yes. All commitment schemes have this problem for the most part.
Yeah.
So I would like just like 1 minute visit back to what the issue was with future Taproot versions. Because I didn't really...
Well, it's actually, I only, during the last several weeks, got deeply into how Taproot actually works. And how it works, that basically, which is well known to everybody, with a Taproot you can spend with just a signature created by a single public key, which can be aggregate of the multiple public keys, like in music scheme. Or you can have a script path pending. And basically you can define multiple scripts up to 2 in 128 power. So basically we are talking about billions and billions of scripts constructed into a Merkle tree. And when you spend using a script path spend, you specify a Merkle tree path to specific script that you will be using, that we will be satisfying with a transaction input witness. And on this script path spend, you are not just using a specific branch of Merkle tree. That is not that well known. Each branch of Merkle tree of scripts have its own script version. And BAP 342 defined just one version of script called TapScript, which may be used with the Taproot. But you may create even today the branches that will commit to a different future script version, which will be activated by a future softworks. And these branches can be spent by anybody, but because these branches are part of the Merkle tree, hidden behind the hash, unless somebody has the whole source of the scripts of the Taproot output, nobody actually will be able to spend that branch, and nobody will be able to know about that, even if it is spent by anybody before the soft fork. When the future soft fork happens, and it creates a definition of a new scripting system, which may be, for instance, quantum-resistant Lamport signatures, or no signatures at all, or something like that, that script path spending gets some meaning under the consensus rule, and this script path spending may be spent under conditions we can have no idea as of today. So there is no guarantee that it will be possible to apply even my refined sign-to-contract scheme to that script path spending. That's the problem with the sign-to-contract spendings of the Taproot outputs.
And there's no way to avoid that this during creation is happening, that you're just restricted to the known, currently known.
Well, again, if before you have created, anyone can spend a script pub key, it's very easy to brute force it. And basically we'll end up that somebody will spend it very soon. With the TapScript and Taproot, with actual Taproot, it is possible to really hide this fact. So there will be script path spendings which will be created, which will be spendable without a signature by even a hash, pre-image of some hash, or like with a Lightning Network Anchor outputs, which actually would not be spent for many years. And when they are spent, if they contained a single-use seals, and we will use only script to sign to contract commitment, they will lose all the single-use seals on that UTXO, on this script plus spending.
Okay.
It's quite complicated, I understand it. Like it took a lot of time of myself to understand how the Taproot actually works on the script level. But it's not just my guess. It's because I was working on the Taproot implementation in Rust Bitcoin. It's something that went through the audit of Blockstream, memory repository, and others. So basically, it's sort of ground truth how it works. So, shall I move to the end sequence proposal that allows to combine all 3 commitment schemes? Actually, there is 4 of them, basically. All of the commitment schemes.
Sure.
Okay, I'll try to. Do you still have my screen?
Yes.
That's actually wrong screen. Yeah. So to use end sequence, we have to see which protocols as of today already use end sequence data for consensus level stuff. And namely, there are 2 of them, replaced by fee, which is BAP 125. And I'm really glad that Peter is here, Peter Todd, who is one of the co-authors of this proposal. So if I'm getting something wrong from it, he can prove me wrong. And the second one is check sequence verify, which is a way how we can verify that certain transaction spends output under relative amount of time, either in blocks or in seconds. And this is defined by BAP 68. There is another BAP related to...
Which should be also Peter, right?
Sorry? Also Peter?
Should be also
I'm not,
Peter, right? It was not check sequence verify.
check block time verify is what I'm responsible for, not check sequence verify.
Yeah. Well, check block
okay.
time verify is also used in Lightning, but it's not the one that we need to touch with the sign to contract or the signaling, fortunately. So check sequence verifying, and finally, additionally to consensus rules, we have to keep an eye that we do not give chain analysis any additional information compared to the one that we are already doing today. So let's start one by one. How replaced by fee encumbers end sequence number? If I'm right from what I was reading from the specification, and I really have these questions to Peter, transaction with end seek which have the value of all bit sets or all bit sets except the last one are not participating in replaced by fee RBF. So they are opt out from it. So we have 2 numbers of end sequence which are not participating, because the standard says less, not less than equal, but less than this number. Am I right?
I'd want to double check the bit to be sure, but I'm like 99% sure that's correct. And the reason why that was picked was basically to make the carve out for non-RBF behavior as small as possible. So basically, like any future transaction would just opt into it accidentally.
Yeah, but you have to. Why you have this FFFFE version?
So that was entirely political, which was to let people use end lock time on their transactions to force the chain to keep moving forward. Right, like something like Bitcoin Core does, and probably a few other wallets, is they set end lock time to the most recent block, so that only the next block can mine the transaction. And that's that's enabled by setting one of the bits of end sequence to to 0, right? So that it's not a locked one. So then the RBF thing was then predicated on it being 1 less than that tiny little carve out to allow you to use end lock time without actually enabling RBF.
That's interesting, because I was really happy that we have 2 options for RBF opt-out transactions. And basically for RBF opt-out transactions, we can use a bit of signaling by just using the last bit. But from what you're saying, it follows that it may conflict with the end lock time signaling.
Yeah, let me think. So, yeah, so like the so the end lock time, right? Like that's always just done by height, by a block height, right?
Mm-hmm.
In the I mean, you can do an end lock time by time, but the way that Bitcoin Core and other wallets, should be doing this is by block height, because block time has, ugly incentive problems. But like the end sequence, that's just the two that was carved out.
So it shouldn't be a problem if we will use the last bit of RBF opt-out transactions as a signaling for using pay to contract or sign to contract skew.
Yeah.
So with a BIP 1 to 5, we have a consequence that we can signal with a 1 bit on the commitment scheme.
But we need 2 bits, right?
No, we did just 1 bit, like set or not set.
But that wouldn't like conflict with the fact that either time locks are activated or not, because as far as I remember, the idea is that if it's maximum value, whatever you put in the lock time is not. It doesn't matter. You still don't have the lock time, and if it's not the maximum value, then the lock time is activated.
Yeah, that's correct. There's only one end sequence value where lock time isn't applied.
Which is F.
Yes, exactly. So they left also another one, so you can have lock time without RBF, if you want.
Right, but if you lock time, for instance, you need to signal the version of non-maximal value, this FFFFFE version. And you, by that, activate the end lock time signaling. But you can always put a lock time, for instance, to 0 and still not activate it.
Well, technically you are activating lock time, but it just doesn't do anything.
Yeah. So you are not in the position when you can't spend some transaction output under conditions you would like to spend, like without efficiently applied end lock time.
So if you use the last bit, don't you have the risk that if you don't signal, then you cannot use lock time in your transaction? Maybe that is something that you may want to do for whatever reason.
Yeah, true. But in that case, you have an option, which may be not the perfect one, that you just opt into RBF and you opt out of end lock time. And basically, you just use the RBF branch of end sequence usage, which I will be discussing in the next slide.
So there's no way to opt into replace by fee without turning on end lock time.
No, it shouldn't be possible as far as I remember.
Yeah.
Well, but again, you can signal end lock time activation without any consequences for your transaction mining conditions. Because if you signal end lock time if you want to use to end lock time, right, then you will have to use RBF. True.
Yeah.
But again, you will set up RBF to the maximal value. You will set up end sequence to the FFFFFFG, and basically wouldn't be able to use RBF. In fact. Yeah,
that's correct. Yeah, so you can use end lock time without RBF, but yeah.
So you have two hacks. If you need to signal lock time presence and you need to go on with the FFFE, you just put lock time FFFF. You just put end sequence to FFFD. If you don't need end lock time, but you have to signal FFFE, you put end lock time to 0. So you mimic the behavior of non-activation with activation route. by providing the maximum of the least value.
Yeah. Now, for maximal, privacy with other ones, you really should just set nlock time to, be only mineable in the next block. Like that's just what most wallets do.
Yeah.
So if there was an actual lock time value for a block, this will not be this will not be obvious fingerprinting for this kind of signaling.
Well, it will be obvious depending on which bit you pick. And also remember, like, no one sets max int and then also sets nlock time.
Yeah, so we will have two fingerprints for rare conditions of when people would like to use one commitment scheme without RBF or the other commitment scheme without nlock time. And these two fingerprints will be the 0 nlock time and FFFFE for in sequence in one of the inputs, or FFFFG in sequence, and
But I mean, so here's a bigger picture question, which is, why have all of this complexity rather than just make the type of commitment to use just already determined by the type of by the thing that picks the single use seal in the first place? It's not really clear to me why we actually need this flexibility.
What is the thing that picks single use seal in the first place?
Well, like in the protocol for single use seals, at some point you define what the single use seal is, and I would move to the way that the single use seal is spent. The protocol used, I would move that one step back rather than have something on chain that actually picks that.
Yeah, well, I was thinking about that option. I haven't put that in slides. Why I discarded it? Like the first one, you can say that this specific asset will always use pay to contract or sign to contract scheme, and we will have the same problems because one assets will be able to be used by under one conditions and other under other conditions.
But I mean, you don't even need to pick it on an asset basis.
Yeah. You can say that I commit to use the pay to contract scheme. Next time I will be spending this output.
Yes,
because
exactly.
I know the output structuring. That's an option, but it reduces some flexibility because, for instance, you may add multiple single-use seals to the same output. You will define an output as an output under multiple protocols as a single-use seal. And what to do if the definition of the spending conditions differ between different assets?
I mean, I think the answer to that is don't do that.
Under certain multi-sig
like
setups,
the software just could, no software should be doing stuff like that,
Yeah, the second is that when you signal with us in sequence, you take the decision at the moment you spend UTXO. When you signal with the client-side validated data, when you define single-use seal, you should do that ahead of time, maybe years.
My argument is just it's so much simpler if you're not messing around with end sequence and other things like that. And you just keep it as simple as we've committed to this particular single-use seal using this protocol, and that's that. And also it's cleaner in the future when who knows, what new ways of doing single-use seals will be added. Because you can always just keep, adding to the protocol all those new ways, rather than having to, come up with yet more ways of shoehorning in bits to end sequence.
Okay, so let's take the option of signaling the commitment scheme in the previous, at the moment of the single-use seal definition. And for the final comparison, I will show that actually you can use in sequence, potentially you can use in sequence without encumbering future soft forks. But let's say, is that true indeed? And if it's not, probably the only option that we will have left is using signaling at the single-use seal definition. So for the second encumber on the end sequence is the end sequence verify thing. And it uses certain bits of the end sequence, namely 31, 22, and bits from 0 to 50. Meaning that the rest of the bits are not used and can be used by us. But again, they can be also used by future soft forks. We can't predict which soft fork will assign a certain bit some meaning. So instead of using individual bit to signal commitment scheme in RBF transactions, I would like to propose to count the number of bits which are set of the unoccupied bit space. And if this number of bits is even or odd, to take decision to the commitment scheme based on that property. So basically, this will maximize compatibility with the future soft forks, and we can tolerate up to 6 future soft forks touching end sequence number.
Still, I mean, we don't know what this, like, that doesn't really maximize it, though, because we don't know what those future soft forks will be. They may still have a restriction that's incompatible with the scheme.
Yeah, true.
You know, and again, like, if you just keep this out of the Bitcoin transaction entirely, well, you just don't have any of these issues. And you don't have to worry about it. You know, and I think it would keep the validation logic simpler, too, where the validation is, well, we just have some branch based on what type of seal this is, and then the rest doesn't have to look at the transaction, you know, in these kind of complex ways.
What about having an option that when we define single-use seal, we say, would we use end sequence mechanism, or we will commit to the future commitment scheme in advance?
I would still oppose that, because again, you know, you still have, you know, yet more, you know, like, you're still baking in this complexity because someone has to implement this, and, you know, all that code has to be written. Or, you know, whereas if you've just said there's different types of seals, you know, I think it just keeps everything a lot simpler.
I think I'm with Peter here.
Yeah.
The question is, this would mean that if you have different assets, that you can only mix them of the same type, right?
Yes, otherwise you will lose some of them.
But that's acceptable, right?
Well, you shouldn't do that, and if you do that, you were notified that with this behavior you will lose assets, like creating an improper script key for transaction.
I mean, there's lots of ways to lose money by committing to the wrong output. So I think this is just a tiny subset of all the different ways to do that, to screw that up. You know, if like your software is picking outputs that it doesn't know it has full control over, you know, who knows like how else it will screw up.
But here is use case. I have an output, and which I own, UTXO, on chain, over the last 5 years. And I assign all the assets to it, which I received over these years, because I have this UTXO. Why should I bother creating new ones? So I have like 10 or 100 assets, NFTs, whatever shit there is, on this same UTXO. And then one day, I decide to fund a Lightning channel by spending part of Bitcoins from that UTXO. And I originally have commit with all those assets to pay to assign to contract scheme. And I found the Lightning channel that use music with the Taproot, and now I'm not able to commit to the spending of those assets on the existing protocols. Well, then I just create an intermediate transaction, I assume, and just solve the problem. I will pay more for transaction fee, but it's solvable.
Yeah. No, I think that's a simpler answer. Just, you know, don't do these things. And, you know, if needed, you might create slightly, you know, more transaction outputs in some rare cases. But like in real wallets, all of this stuff's going to be hidden from the user anyway. You know, they're not going to be making decisions like this anyway. So.
And I envision that probably even for real use of RGB someday, I would use a completely different derivation path for the for the wallet.
Well, when you don't need the relation part when you define the single-use seal. So you still can assign. Nothing prevents you from creating single-use seals from UTXO that existed for 10 years before now, created with a completely different duration path. But again, if you do that, you just pay more fees for.
Yeah, I just don't see this reusing UTXOs as particularly useful use case, because I just don't see wallets actually doing that.
Yeah. Okay, so basically it seems like we are moving towards having no signaling on the end sequence level and instead a signaling of the single-use seal definition at the single-use definition time.
Yeah, I think that makes a lot more sense.
Yeah. And it makes go on.
Sorry, with definition, that means that one specific asset could only use one commitment scheme.
No,
right?
no, not asset. When you create a state transition for RGB, you basically say in that state transition that this specific output, which is defined by single-use seal, must use a pay-to-contract or sign-to-contract commitment in the future.
Okay, because I remember a similar idea being proposed in order to select the specific output that was including the pay-to-contract, but then we discarded it because we found some double spending surface there. How is not the same here? I'm trying to understand what the difference was in that case.
In that case, we had only a single commitment scheme, which is pay-to-contract, and we commit to the transition that defines a transaction output in the transaction output. So we have this feedback loop, and that's why you can cheat.
But if we do that in a step before, just like we are doing here?
Yes, step before, and you're committing to a step before today, and tomorrow when you spend it, you have to follow the commitment that you have created yesterday. So you're not committing at the moment of performing the transaction. You're committing before that. Because again, you commit in the state transition, which is committed as a message into the closing of the single-use seal into existing transaction mined in Bitcoin blockchain. And it is a ground truth for everybody following that blockchain. So when you spend that single-use seal, you can't change that truth or show two different truths to different parties. When you commit to transaction output in pay-to-contract scheme, you do that commitment at the moment when you create the transaction and transition and the message over which you close the single-use seal. So nothing prevents you from creating two different commitments in the same transaction, mining that transaction and showing two different truths to different parties.
Yeah, sure, but why couldn't I'm not defending this case, just trying to stress it to understand the difference. Why couldn't I just say that in this transaction that I'm in this in this basic transaction, RGB transaction I'm making now, I am saying that the guy that will spend this kind of asset after will have to put the commitment in the output number 3 modulo the total number of outputs. So I could delay I could create the decision now that will affect the feasibility of the state transactions later. That will basically be the same as this strategy that we are proposing now, or not?
No, it's not the same strategy. First of all, if you are paying to a party who would not like to tweak their private key, and you can't create a transaction that wouldn't require them to tweak the private key, you just create an intermediate transaction spending yourself to yourself that changes the commitment scheme.
Exactly. Yeah.
Right. Yeah.
And once you created that, you have a different commitment scheme, and you're already committed to that commitment scheme, and that is the ground truth for all future owners of the assets. So you can't double commit
Mm-hmm.
or double spend, from what I'm seeing here.
Okay.
The rule of thumb is if you do something in the transaction output of the transaction that is not yet mined, you can double spend. If you do something in the transaction output of the previous transaction you are spending from, which is already mined, or you doing something in the transaction input, you are not that fact because you have just a single option. The question is if you have two off-chain transactions. That's the more interesting situation, like in Lightning Network. You have a graph of transactions, which is not yet mined. But again, you need signatures. So it's not about mining, it's about signing. So if you have a signature in the transaction input, you're basically committing to both the current and the previous transaction structure. And unless you put something in the transaction output, you can't create a double commitment to that. So if you have a signature of a certain transaction of chain, that is still final transaction because you can make sure, if it's of course, mutually signed transaction. So you're spending a funding input, which is 2 of 2 multi-sig, for instance, and you have a signature of the other party. There is no way that the other party can publish an alternative transaction because it doesn't have your signature on it. And basically, it is the same security as the mine transaction. So do we all agree, or there is some concerns that this is really indeed secure?
I wonder if this would even leave the option if for some reason, maybe in the future, we come up with a third commitment scheme, that it would still allow this to be added, because with the log time you suggested, it would only have 1 bit. So it could only support like two schemes, and if we move it to the opening of the seal, then.
So you're talking about that. What if we will allow people to choose between pre-committing to the commitment scheme with the previous, when they define single use seal, or pre-committing to specifying the single use seal by using n sequence number? So is it what we're talking about?
Yeah.
Well, like theoretically, that is, I think this is interesting, and I actually was the one that proposed this. But let's think about the real world wallets. They need to have an algorithm, which of these ways they will use. And we will end up that one wallet will always use one algorithm and the others will always use the other algorithm, because there is no rational which one to use. And if we're basically taking the risks of both of the routes, because if some soft fork will happen that will disallow us from using a sequence, half of the wallets will be fucked, half of the wallets will survive. If we will have security leak discovered, the other half will be fucked unpredictably. Like it's really doesn't add any security to the scheme, I think. Or we should define a certain criteria which wallets should follow to select specific way of committing. But again, I agree with Peter that basically it adds complexity, increases attack surface, and doesn't add more usability at all. Like if you've done something wrong with your single use seal definition, just use intermediate transaction. If you created multiple single use seals on the same UTXO, committing to different commitment schemes, yes, you will use some value, but basically that's what wallets are designed for, to prevent improper usage of the protocols. Because you can do the same by creating a script output, the script pubkey.
Did we lose him?
Yes.
Looks like.
Maxim? I was hoping so much it was just my problem.
Nope, he seems lost to me. Green's cut out.
Hi.
Hello.
We've lost you for the past 2 minutes, one.
Okay, sorry. I was talking all the time. It's something wrong with the GPU or screen.
Maybe, but we didn't hear you also.
Okay, basically I wasn't saying anything new.
Okay.
I agreed with Peter that the introduction of more features is basically increasing the attack surface.
Maxim, maybe you could share your screen again. Because I cannot see it. Maxim, if you're try to reconnect, because I cannot. Yes. Boom, boom, boom. Okay, Maxim, unmute yourself.
Hello, do you hear me?
Yes, we can, but we do not. Okay, now we see your screen.
Yeah, something goes wrong with everything.
Yeah, it happens. Never mind.
So the point we arrived to is that Peter Todd proposal on not using n-sequence signaling, but instead committing to the specific pay-to-contract or sign-to-contract scheme at the moment of single util definition seems to be the most reasonable one.
Yep, sounds good to me.
Yeah.
Giacomo?
Yes.
And Federico, who is also
Yeah.
Yeah, okay, so let's stick with that, because actually I wouldn't go through this slide, but it's just to show that with a Lightning Network, how it uses n-sequence, it's even more interesting. Just today, when I prepared the slides and I was looking again into the bold specifications, I found that what can seem to be a vulnerability of the Lightning Network is actually it uses RBF in an improper way. It sets up 24 lower n-sequence bits in the funding output, which is used then by the input of the commitment transaction to the random actually number. So basically, not just the 6 lowest bits, but 24 bits, including type flag. So basically Lightning Network, from the specification and consensus rules that I know, it follows that some of the commitment transactions will randomly use either block numbering or time numbering for n-sequence, which is really strange. So I probably will open an issue tomorrow on this matter. And also it looks like that the numbering of n-sequence with each channel update is not deterministically incremental, because they're XORing some certain predefined random number with a commitment update number. And it doesn't look like to me that this will always increase, because with XOR procedure, you wouldn't have always increasing the number, which is quite weird. So I'm not sure that this is a bug, but it certainly looks like a bug. Also, it's quite very random use of RBF with this end sequence number and no other outputs. Like sometimes they use 0 as a constant number. So basically this is analysis. So first they use randomly end sequence number, sometimes using pseudo-random numbers, sometimes negotiated values, sometimes fixed constants. And also with some features they introduce, they change this rule, so it's very, very unpredictable. And it will be really hard to combine any end sequence related rules, which are even contradictory to the consensus rules, with the Lightning Network. So my proposal was to just redefine that in Bifrost, but we don't need that if we will not use end sequence. So it just adds to the Peter Todd argument that we shouldn't use end sequence signaling and instead pre-commit to the specific scheme at the moment we create a single-use seal. So the summary of the proposal from the today call, instead of end sequence value, we use take the value from the single-use seal definition. And if it is signals sign to contract commitment, we do sign to contract verification. If it signals pay to contract commitment, we have three options. We first of all use LNPBP3 to detect the specific transaction output that will contain the commitment. Nothing changes here. If this output is a script pub key, we use LNPBP2 procedure standard to extract public keys, set of public keys which will group commit by their sum to certain value, to certain message. If it is pay to taproot, we use a slightly modified procedure because pay to taproot is by itself a pay to contract commitment. So we apply our single-use seal commitment to the internal key of the taproot. Then on top of that, we apply the normal taproot commitment. So it's a modified scheme of the pay to contract, which I named tap to contract. It's also already a part of LNPBP standard, so it's covered. And finally, if the output is actual op return output and not some script pub key, we just treat this op return output as containing a commitment. And we extract the data from this output depending on specific algorithm and just verify the commitment. So basically this part, the right part of the scheme, is already covered by existing standards and part of RGB implementation. The only thing that we do not have is a sign to contract implementation and this part of the route. So we need to add choose of the commitment scheme in the single seal definition and create a sign to contract story. And the sign to contract probably will be the topic of our next dev call because we don't just have time today. And there is a lot of issues in designing sign to contract, and especially in relation to U6. The only action points that I can name today is that I started first drafts on them, so you are invited to join that if you will have time and desire. It's starting with numbering with the 19. So 19 stands for sign to contract tweaking of multiple signatures under the CDCA scheme. 91 is Schnorr signatures, tweaking of multiple because witness can contain multiple Schnorr signatures, even unaggregated. That's an important point because you can do that with the taproot. And 92 is actually how you will put that instruction inside the witness data. So these are standards that has to be written and designed. Also, you may review and contribute to finalization of this TXO single-use seal scheme, which we discussed throughout today. This is the pull request, current pull request. If you'd like to, you can revisit the previous work on the pay-to-contract commitments that we already done so far. It's more like finalized, multiple years, multiple eyes has looked through that, and there were multiple reviews. But again, it's never too late to find a bug. And finally, the most important, implementation of sign-to-contract stack, which requires modification on SEC P256K1 library. Fortunately, Jonas Nick has from Blockstream, he already had a previous attempt of implementation of it. And I'm trying to rebase his attempt on top of master, when now master contains the final version of Schnorr signatures. So this is the pull request of that attempt. After that, we will need to port this into Rust SecP library, and finally to use that in the single UCL implementation that we have for Bitcoin protocol. To finalize the call, for those who will be looking into the standards, not to be missed out, they're basically layers. These standards are organized in layers. So there are standards related to pay-to-contract, commitments, which are upgraded for the case of use of scripts in the script.key outputs or multiple public keys and so on and so forth. So these are three standards, LNPBP 1 to 3. We have to design the sign-to-contract standards, which will be numbered from 90 to 92. And we have this LNPBP 4, which defines how we can commit to multiple messages under multiple protocols in the single commitment that goes into single UCL. All three of these things are united under the umbrella name deterministic Bitcoin commitments, which defines how they actually, this whole algorithm that we were discussing today, how we will define which specific commitment scheme will be used. And together with the single UCL's API, which is not Bitcoin specific, it's basically the proposal written by Peter Todd originally, structured it as a standard called LNPBP 8. Together they constitute the final Bitcoin transaction output based single UCLs, which is LNPBP 10 standard. And you can find it in this pull request that I just mentioned. And the implementation of this stuff on top of these standards goes in Rust language. It can be found on kratis.io or read the documentation on the docs.rs. The names of the kratis can be taken from these slides. So if you will need to, you can always refer once this call will be published online with the slides and video recording. That's all on my part. So if there is anything else we can discuss on this matter, let's proceed to that.
Awesome. Thank you very much, Maxim, for such an exhaustive and pretty deep dive. Guys, if you have any questions, feel free to drop them now. I know you're tired, but it's better to do it now, probably. So no questions?
I don't know about you, but I'm looking forward to my long-delayed lunch.
Everybody is exhausted, I think, after this. But we have a good finalization that all of that can be simplified again, because Peter Todd said that you're over-engineering everything.
Yeah. The beginning of the code was very scary, and now I feel better. Thank you, Maxim. Thank you, everybody.
Thank you, everybody, for finding the time.
Thank you.
Thank you, guys. Thank you for attending, Maxim. Thank you for the presentation again.
Bye.
See you in 2 weeks.
Yeah.
Bye-bye.
Bye-bye.
Bye. Thank you, guys.
Thank you. Bye.